Hello, welcome back to our Jörn YouTube channel. My name is Reinke. Today, as you can see, we're back in the office because today I will give you a little bit of theoretical input. I want to talk about rubber metal parts and condition monitoring. Okay, here we are, condition monitoring. What does it mean? Condition monitoring allows you to do a condition-based maintenance planning. I mean, the matter of today, the subject today is you do reactive maintenance, so you change the parts when they're broken, or if you know a little bit more about load data and load capacity of your parts, you do preventive maintenance. So that means you do testing, you do endurance testing in a test rig and compare the results with the load data measured in the field. And based on that, you plan a certain lifetime for the part in the vehicle or in the machine. The future is going to be condition monitoring system. This is available already for some components and it's proven and it works. However, it does not exist yet for rubber metal parts. And then the Champions League, so to speak, in football words, is doing predictive maintenance. So predicting when the parts will gonna fail. So to predict the remaining useful life, that's what I call it. Why is that? What's the reason for that? I mean, I want to show you something. This is a typical diagram on a hydropulse test rig and a test bench for a rubber metal part. You see in the beginning of the part a quite significant increase of the amplitude, which means a decrease of stiffness in part, and the decrease of stiffness is nothing else than just wear or beginning of failure. After the first reduction of stiffness, which is due to creeping and these factors, you have a rather flat and stable condition where you have just minor changes of the stiffness, and then at the end of the lifetime you have a quite progressive stiffness drop, and that's the area when you have to start planning your maintenance, your replacement. I mean, what you see here on the graph are just examples of one part type with different loads. That's why you see a huge spread. But however, in reality, even if you test one part or different parts from the same production lot, you have a quite big spread. This is due to the fact that rubber, which you're using, is mainly natural rubber. So that means it's a natural raw material, and that has a huge tolerance range. And if you want to be on a safe side of your system, you have to do a very conservative design. That means you have to make sure that almost 100% of your parts will overachieve the limitation of the load spectra applied to the part. And that means the weakest part should be in the area of, with this load capacity, should be in the area of the load applied to the part. In other words, the best part would last twice as much or even longer than that. So that means replacing such a part would be a waste of money, time, resources, and of course that leads to significant downtime of your machine. Considering a bogie of a train, I mean, the whole train must come to the service and standing still, and it would be not available for service, for the job it's going to do, transporting passengers. Or considering a wind turbine, for example. I mean, if you want to replace a gearbox mount or a generator mount, that's a significant maintenance work you have to do. So that means you have to plan that very carefully in order to keep the downtime of the whole machine as low as possible, but you still have hours or days where it's not in service, and you have to send somebody out and up to the turbine for replacement. So that's significant cost if you do that too frequently. So it's better to do that on demand, so to speak. And that's what is possible with a condition monitoring system. So far this did not exist for rubber metal parts yet, but now it's changed. We've developed such a system, and the first thing we did was developing a physical property which is representative for the fatigue of the part. Of course, remembering what I've just said, it's the stiffness. However, you can't measure the stiffness. You can measure displacement, but that's rather complicated. Or you can measure acceleration and difference in the vibration behavior, different shifting eigenfrequencies or eigenmodes or such, but that is very complicated. We've worked out that the temperature is a very good physical property which can be easily measured and is very good correlating with the stiffness. And there are some advantages of the temperature. Doesn't matter which direction the load and the displacement is applied to the part, the temperature increases when the cracks are occurring. That's easier. If you considering accelerometers or displacement measurement, you have to think before, you have to understand before very clearly in which direction you expect the main movement and the main loads. Okay, so now it's clear why the temperature is a very great physical property. Of course, you say, well, what if the ambient temperature will change? You're right, so that's why we take the temperature difference between the ambient and the temperature in the inner part of the rubber. Of course, that still has a little bit of an influence, but it's significantly reduced. Here you can see some pictures and some diagrams of data we've collected. First, you see in the left corner a detailed picture of the test bench, where the bush is in a fixture installed, and the hydropulse cylinder is on the left side, and the force is going to be applied to the part, oscillating, and normally, if possible, we run that system to the failure. In the lower part of the diagram, you see a heat chamber. We also applied heat in the right side. You can see some diagrams where the temperature, even the temperature difference, shows lots of peaks. That has many reasons. Number one is maybe we changed the test conditions, or in some areas we just switched off the test bench overnight because in some tests couldn't be operated overnight, and that's of course under that circumstance the part cooled down completely. On the lower part you can see a typical slit bush. What a slit bush is something you know already, and if you forgot, please go back to our video about slit bushes. And you can see the cable coming out of the outer tube, that's the temperature sensor. A thermocouple or temperature sensor has even more advantages. I mean, it's the most advantage is, beside the physical property of the part of the rubber metal part itself, a thermocouple is rather cheap. The electronic you need to evaluate the data is cheap and simple, because you measure the temperature at two different positions, comparing those temperatures, and that leads to a difference of the electrical voltage. Very simple technology. Here you can see some typical curves. On the left side you see a test which was not successful, to be honest, because the test was stopped for any other reasons. But you can see first in the beginning the increase of the temperature correlating very well with the increase of displacement, Then you see a decrease for whatever reason and a flat area. And on the other side, you can see this very bumpy curve. But that works, you can evaluate that. However, it's going to be a little bit more difficult to do so because of the very severe bumps. But at the end of the measurement, you see again the increase of the temperature difference. That is very, very significant, and that allows you to also evaluate these data, even though it's more tricky. Here you can see many results we've gathered during all the test sessions, and we compare here the point of time when our system gave a warning saying, okay, the rubber metal part will fail soon. We've compared this with the lifetime which we achieved in reality. And of course, we use that to calculate the error. Of course, you can say the error itself should be minimized as well, but you also have to consider, is the error on one side or on the other side? So it makes a difference whether the warning comes a little bit too early or a little bit too late. Coming a little bit too late is much worse than coming a little bit too early, so you need to make sure that the warning comes before the part would fail in reality. That's what we show here. So you see in the blue column the real lifetime, and in the green the time after the warning. Okay. In some of the results you don't see really a difference. That's why we've shown that here a little bit more clear. Here you can see how many percentage of the real lifetime the warning came. And that shows you that in all the cases the warning occurred before we've achieved the complete lifetime. So we have been on the safe side. And I believe, the worst result came at about 80% of the real lifetime. This is something great, honestly speaking, considering what I've said before. If you do a conservative design of this part, you have in many cases replacement of the part after 50% or even less of the real lifetime. So that means not only wasting lifetime of the part, but also meaning that you have a replace event much too early and too much. Yeah, that shows that our system would be able to help saving costs significantly in maintenance, the overall cost. And the maintenance cost is not in the spare part, it's more in the work to be done to replace the part, and in some cases even worth in the time where the machine is out of operation. Yeah. Okay, as I've mentioned before, that is a research project we've done together with the University of Paderborn with the professor for dynamic and mechatronic. The research project was sponsored by the Federal Ministry for Economics and Energy in Germany. And we've closed the research project, so we're now in the phase where we do the development and apply these technology to real applications. Could be yours. That's it for today about condition monitoring. And the nature of research and development project is that we generate new content, so that's why I can invite you to stay in touch with us. Please contact me if you have any questions, if you want to get more information about what we're doing. And of course, if you want to keep informed, please subscribe our channel or contact me at any other social media channel. You will find all the details, all the contact details in the info box downstairs. I will not close without saying thank you much to my colleague, to Michael Schiebel, who's the man behind the camera, and he promised me he will show up in front of the camera as soon as we have 100 people subscribing our channel. But however, my goal is I want to achieve 1,000 followers, 1,000 people subscribing us. Thank you very much. See you next time. Bye bye.